Hi everyone, welcome to the first of a little two-part lesson that we're going to be doing this week. I've broken things up just to make it a little bit easier. So we're going to start today with chemical and word equations, and then later in the week we're going to do part 2, which will be about balancing chemical equations. So you'll want to grab the note that I posted on Google Classroom that goes with this, or a blank sheet of paper, and let's get started. Okay, so I want you guys to think back to when we were in class, feels like ages ago, and we did those stations around the room where we looked at chemical and physical changes and looking at what kind of observations we can make that indicate a chemical reaction has taken place. And when we did that mini lab, we came up with a definition for what a chemical reaction is. So we're just going to remember that. So a chemical reaction is when one or more substances changes into different substances. So that means that we are producing at least one new substance. And if you think back to that lab, there's a few ways that we can tell that this has happened. If we have fire or if heat is produced, if we have light being produced, if we have a color change, if we have a precipitate forming that's solid, or if we have bubbles. Those are some of the observations that we made that tell us that a chemical reaction has taken place. So this idea that we're creating new substances is going to be really important today. So what are chemical equations? We use them to describe chemical reactions that are happening. And we've got two different ways to write them. We've got chemical equations and word equations. They mean the same thing, and this is why we've been practicing so much going back and forth between chemical formulas and chemical names, is so that we can put that together and create these two types of equations. So we have to remember that all of the ionic and molecular naming rules that we've been practicing and working on, they apply when going in between these two types of equations. So we don't want to forget everything that we've just learned. We have to use all that for this next step. So let's kind of break this down. Let's look at the different parts of an equation. So this right here is a chemical equation, and basically it tells us a story of the reaction that's happening. So I've color-coded it to kind of break down the parts. So this is called a chemical equation. And like we just said, there's two ways to show an equation. There's this way, or there's a word equation. And so that would look like this. So our chemical equation has C plus O2, little arrow, CO2. And we can translate that into words. So what this would translate to is carbon and oxygen gas produce carbon dioxide. So you read it almost like a sentence. And so if we break this into parts, you can see I've kind of color-coded it. The first thing I want to point out is that on the left side of an equation is where we find our reactants. And reactants are substances that are used up in the reaction. So this is basically what you are starting with. You start with your reactants. They're going to be reacting together. Then on the right side of an equation, we find our products. So this is what's being produced in a reaction, and that kind of makes sense, that name, products being produced. So this is what you're going to end up with at the end of your reaction. And then the other two things that I just want to point out is that in an equation, when we have a little plus sign, that means and. So you might hear sometimes combines with. So you could also say carbon combines with oxygen gas. Either or, that totally works, but that plus sign means that there's a combination happening between our reactants or products. If you see a plus sign on the product side, then that just means you have more than one product. And then the arrow here means produces. So that's saying that whatever we combine on this left side is going to produce everything that we see on the right side. So our reactants produce our products. So let's look at some examples. So if we are trying to go from chemical equation to word equation, we have to remember all of our naming rules. So basically you can split this up into different chemical formulas. So if we look at the first one here, we've got K and F. Well, we know that's potassium, and fluorine, that's an ionic compound because potassium is a metal. There's only 2 elements, so it's not a polyatomic, and potassium is not on our multivalent list. So this is just a normal ionic compound. We're going to use our normal ionic naming rules, and that would be potassium fluoride. We're going to go through that same process for this one, and this one. We don't have any polyatomics, molecular compounds, or multivalent metals going on here. It's just very simple ionic compounds. So we name them normally. So this translates to potassium fluoride. This here, MgO, magnesium oxide. K2O is potassium oxide, and MgF2 is magnesium fluoride. And so then once you have those names, you can kind of go back and fill in, okay, wherever I see a plus sign, I need to write and. Wherever I see a arrow, I need to write produces. So Kf plus MgO, arrow, K2O plus MgF2, that's the chemical equation. The word equation would translate to be potassium fluoride and magnesium oxide produces potassium oxide and magnesium fluoride. And so our reactants were Kf and MgO. So again, reactants are on the left, and our products were K2O and MgF2 on the right. Let's try another one. Maybe pause and see if you can figure this one out on your own first, and then press play and we'll see if we can get it right. So CH4, those are both non-metals. So we have a molecular compound here. We have O all by itself bonded to itself because we have O2. So try to think about what that means. We have CO2, also a molecular compound, and H2O, also a molecular compound. So we have 4 molecular compounds here. We're going to want to use those prefixes in the names to let us know how many there are. So this would translate into this word equation. Carbon tetra, remember adding those prefixes in, carbon tetrahydride and oxygen gas. Remember, whenever we have an atom bonded to itself, we say oxygen gas. Produces carbon dioxide and water. Our reactants were on the left and our products were on the right. So let's go backwards for our last example. Now I have the word equation and I'm going to be trying to figure out the chemical equation. So for this we have to use all of our rules. We have to use our crisscross rules. We have to, if it was molecular, we'd have to use those prefixes. So let's see what we have going on here. We have iron and sodium nitrate produce iron 2 nitrate and sodium. So there's a couple things right off the bat you should notice here. First of all, sodium nitrate. This doesn't end in "ide," so that means it's a polyatomic. We got to check the back of our chart. And the second thing that pops out is we have iron 2. So that's a multivalent metal. So we've also got to check that chart for this one. So let's see what it translates to. So iron, whenever a metal is on its own, that's all we need to write. We just need to write that metal. So iron is Fe. Sodium nitrate. Sodium is Na. Nitrate, if we look at our chart, is NO3. They both have a 1 as a charge. Sodium is +1 and nitrate is -1. So if we crisscross that, we don't need to write those 1s in there. We're producing iron 2 nitrate. So iron 2, remember that tells us that there's a little +2 on the iron. Nitrate still is just a -1. So when we crisscross, that 2 comes right there. And then we have sodium on its own. So that is the chemical equation translated from this word equation. Our reactants were iron and sodium nitrate on the left side, and our products were iron 2 nitrate. Oops, there shouldn't be a bracket there. Iron 2 nitrate and sodium were our products. So that was a little bit fast. Really, we're just using those exact same rules and trying to write them in a sentence. So you're going to have multiple naming rules to think about at the same time when you're going from a word equation to a chemical equation or vice versa. So all those same rules, we're just trying to apply those to a bit of a bigger example. So I have practice on the back of that note. So take a look at that. I will post the answers as well so you can check as you go, and then stay tuned for part 2 later this week.